actually has an advantage of a factor of 5 in terms of the amount of kind of thermal energy created per neutron. And this actually means that you can have, for example, the Spallation neutron source in Tennessee is a 1.4 megawatt spallation source, but it actually creates time average amount of neutrons, which is similar to what you have at a high flux reactor, except it's now created in pulses, which is very valuable experimentally. So that's the distinction between these two different methods. And here's a chart from actually some time back, which shows you the flux of thermal neutrons available as a function of year. And so, here's the discovery by Chadwick of the neutron, and then it comes up here, and there's a long era in the 80s, 90s, etc., where all of the work was basically being done at fission sources. And then there's the advent of using spallation, in particular pulsed spallation sources, to generate pulsed neutron beams. And that has actually created sort of a new trajectory that is steeper, and so we're able to get brighter neutron beams using the spallation method, really because of being able to condense in time the pulses of neutrons. Okay, all right, so then this is where the experiments go on. All around the world, there are various, in Europe, there are, I guess, 4 or 5 different places that people are now doing neutron experiments. There's a new facility being built up in Sweden here, which says ESS. That's going to be a 5 megawatt spallation source. Australia has a facility. There are facilities in Asia. And these are the facilities in the States, NIST, and the 2 sources at Oak Ridge National Lab. And there's also a source up in Canada. So if you're an experimentalist doing neutron scattering, you'll be basically traveling around to these kinds of places, for better or worse. These are the facilities in the States with little pictures of each. That's the spallation source in the Los Alamos lab. These are the these are the sources at Oak Ridge National Lab. That's the spallation source. That's the reactor facility. And here's the picture of the neutron fission source at NIST Center for Neutron Research. And here's the one up in Canada. Okay, here's a picture of a typical research reactor. You have the fuel rods and the core of the reactor, which is, in this case, a heavy water reactor. So it's D2O cooled reactor. You can ask if you're interested, but we won't really get into kind of the details of how everything works. But I just want to show you that basically you've perforated the shielding with tubes through which the neutrons that are created in the fission process can sort of escape. And so you have essentially a Boltzmann distribution of neutrons coming out of these sources. And the characteristic temperature is the temperature of whatever material is the last point of scattering. And for a thermal source, it'll typically be water held around room temperature. For a cold source, we'll be using hydrogen or deuterium to actually physically cool down the neutron gas. And there's a little hint, cooling is actually good, because that's the one way that I can remove entropy from the system, which corresponds to having a brighter source. So it's good to condense in time, and it's good to cool down. And so we do both of those things both at reactors and at spallation sources. Okay, here is kind of an outline of what a facility such as NIST looks like. Here's the reactor. There are various instruments around the facility itself. And then there are these refractive guides that are based on this principle, which basically transport the neutron beam to a rather, it could go as far as 40 meters or 50 meters, 100 meters, even kilometers. Not in this case, but people talk about making kilometer-long guides. And you have almost no losses because you're just doing this refractive process along the way. And this allows you to basically have many more instruments looking at the same facility. You could never pack all of these things in here. So that's one of the tricks. Okay, let me find a couple of pictures of actual instruments. I'll show you this picture of the spallation neutron source, which is actually the newest source that we have in the States. But then let me show you a couple of pictures of instruments. All right, so here is basically in the 50s and 60s when people first discovered that neutrons could be used to probe structure and dynamics. This is what it looked like. And now there are all sorts of different instruments which are all basically doing diffraction. So they're measuring this diffraction cross-section that we talked about. They look different, and that's because they access different parts of momentum space. So the technicalities are somewhat different, but in the end they're actually measuring the same kind of thing. And I just want to show you a pretty straightforward instrument that is used for measuring Bragg diffraction. It could be magnetic or nuclear Bragg diffraction. And basically behind this shielding is a monochromatic crystal which is reflecting neutrons of a certain wavelength to the sample, which is sitting here. And then the sample scatters neutrons, and those neutrons are detected in this array of detectors. In this case, I think there are 32 detectors. These are the little amplifiers which are amplifying these charge pulses created by this helium-3 proportional counter. And then they will each be looking at different angles of scattering. And this detector will actually be able to move a little bit to probe, to map out a whole continuous range of scattering angles. So that's an instrument which measures as a function of angle of scattering, but it doesn't actually distinguish the energy of the neutrons. It takes any energy you would like. And so it becomes, however, dominated by the so-called elastically scattered neutrons. Those would make up maybe 95% of the scattering. And so this is a good machine for measuring just elastic scattering. Okay, all right, so then I would like to show you a example of what has happened in inelastic scattering. And here's a picture of one of the grandfathers of inelastic neutron scattering, Bertram Brockhaus, Nobel Prize from '94. And he's sitting at his instrument, which is an ingenious invention that he made. And here's a picture of it. The first machine. So basically he has one crystal to select the energy of the incident neutron, and then another crystal sitting here which will only be able to Bragg diffract neutrons of a specific energy, which will be the scattered neutron. And then by choosing a different angle of scattering here and here, he can select a different incident energy to final energy. The sample sits right at this location here, and so in order for a neutron to make it all the way from the reactor to the detector, it's going to have to come in with an energy which is different from the scattered energy, and it will have to deliver some kinetic energy to the sample. So he keeps track of the inelastic process using a monochromatic and an analyzing crystal, and so that kind of method is still used today, but the instrumentation looks quite different. It's just proliferated using various different tricks of the trade, which allow us now to go all the way from basically microelectron volt, tens of microelectron volt resolution on this instrument, up to energy transfer of 1 electron volt or even more on these kinds of machines. So it's become a much more kind of diverse set of experiments one can carry out using inelastic neutron scattering. And maybe I will show you. Let's say, let's see. Okay, so since we're almost at the end, I just want to show you an example of what a modern so-called time-of-flight inelastic neutron scattering instrument looks like. So this machine is about as large as the entire floor here. You know, it has more or less the size of this volume down here. And back here is the pulsed neutron source, which is the Spallation neutron source, so the 1.4 megawatt Spallation source. And it has protons interacting with liquid mercury, creating pulses of neutrons. And those neutrons are being moderated by a suitable water moderator in this case. And it's then creating pulses of neutrons covering the energy range maybe from 10 millielectron volts up to 1 electron volt, which are coming down this flight path here. Now, the high energy neutrons are moving really fast, and the low energy neutrons are just moving along slower. The typical velocity, just to get a sense of it, is thousands of meters per second. So it's kind of the velocity of a bullet. It's not faster than that. And so as they travel down this track here, they actually spread out spatially. And then what happens is that at this particular point, there's a so-called Fermi chopper, which will open up and then close again. We won't get into the details of how it works. It's actually a rotating device. And so it admits only the neutrons that arrive at that location at a specific time after having been created at the source. So in that way, you actually end up in this location with a monochromatic pulsed neutron beam. And that interacts then with the sample, and neutrons will scatter towards this huge bank of detectors. And using the same method that I described over here, the time of detection will be registered. And from the time of detection, I will know how long time it took for the neutron to travel from the sample to the detector. I know the distance, so I can get its velocity, so I can get its kinetic energy. And so I can calculate from the time of detection energy transfer. I know the incident energy, because I know the functioning of the chopper. I know when it arrived, so I know the final energy. And this becomes then a measurement of the difference in kinetic energy in the scattering process. So it's as simple as that. And the wave vector transfer I get by just taking the vector subtraction of the incident momentum and the final momentum. And this will now be a measurement which is fundamentally a four-dimensional measurement. Now why four? Let's see if we can work it out. So one is the energy transfer, which we talked about. The other two dimensions would be where on this area of the detector did the neutron arrive. And so that gets me to three. The fourth dimension is what was the orientation of the sample. So I can rotate the sample, and that will, so those become the natural four dimensions of the experiment. And what we do then is that we basically transform those four angular and time variables essentially into momentum transfer and energy transfer, and so that we can measure a scattering cross-section as a function of energy transfer and momentum transfer. And let me just show you a picture of, this is kind of a cool picture of inside the detector bank. So the sample will be sitting, this is actually the tube pointing straight at you where the neutrons are coming out. This is where the sample would be. And then these are neatly organized detection tubes, which are also position sensitive, so that I know whether the neutron arrived here or down here. I can keep track of that. And I can also keep track of which of these many detectors were hit, so I know exactly where I was detected on this entire huge detector. That's what it looks like. And then what the actual data looks like, we're going to talk much more about that both tomorrow and Thursday. But here's, I don't know if I can get this to. Yeah, here's, we always have the challenge of representing a four-dimensional data set. So what is shown here is actually as a function of energy transfer, which you see up here, what do the structures look like in momentum space. So in this data, there will both be information about the Bragg intensity and information about the dispersion relation for phonons and magnetic structures. All of that is kind of packed in there and needs to be disentangled by the experimentalists to find the interesting physics. Okay, so then to summarize, I'm going to put all the slides up so you can take a look, but we think that neutrons are really an indispensable tool in hard condensed matter physics, and we can probe basically structure and dynamics, both chemical structure and magnetic structure. We are in a period of tremendous gain in the performance of these instruments, so that we've gone from a case where you could sort of measure point by point in a four-dimensional space to a situation where we really do measure the whole cross-section in the four-dimensional space. And this has given rise to a period of rapid evolution in how to actually analyze and think about the data, as well as how to plan experiments. And I'd really like to encourage those of you who have experimental inclinations to think about using the technique in your work, and for those of you who have theoretical inclinations to take a look at some of the papers that are coming out and see how you might be able to couple to that kind of information. And lastly, I want to point out that, particularly if you were kind of interested in getting involved in this kind of work experimentally, that these are all user facilities, which means that to be able to do experiments here, we write basically proposals for experiments. Those are submitted, the whole online process and things like that. There's a review committee that looks at it, and then you can be awarded beam time to do your experiment, or you may have to write a second proposal to eventually get in. It's reasonably competitive, but there's a lot of interest in engaging a larger community of users, and there's a great interest in working with young people like yourselves. And so it's actually not that hard. If you're working in, maybe you're using magnetization measurements or transport measurements, some form of bulk method, maybe you're doing synthesis of materials, it would be not at all a stretch to say, let me try, what can I learn about the magnetic excitations in this material? I'll write a proposal, and you will find pretty good guidance from the scientists at these facilities to direct you towards the instruments that will be more useful for your work. Oh, okay. All right, I think I should stop now, and I can take any questions, or we can talk during the break. Thank you very much. Yes?
You mentioned how to detect like antiferromagnetism by looking at the additional bragg.
Yes.
Can you detect like bond order waves, or like
Bond order waves?
Correlations between the two sites?
Sure. Anything that involves the spin operator, basically, we will be sensitive to that. And so I could give you specific examples. So if I have let's say that I have a formation of a valence bond crystal. So then basically, what I would say is that okay, sorry about that. So let's say that I have a valence bond crystal. So I might go from high temperature, where I have a fourfold rotation axis here, and then I end up forming singlets in this kind of pattern here. This kind of pattern, like that. This situation here. So now I've broken my fourfold rotation axis. I don't have a finite expectation value of the spin on this side, but I do have a singlet that is formed between these particular sides. So that kind of structure has actually increased the size of the unit cell. And what I'm going to see in that case is that I will be able to I will not see any elastic scattering from this structure. Well, okay. I will not see any elastic magnetic scattering from this structure because there's no static expectation value of the spin operator. I will see a doubling of the structural unit cell because there will be a little bit of difference in this spacing compared to maybe I'm out of battery, compared to this spacing here. And so I will see probably new Bragg peaks that will arise, which will be new nuclear Bragg peaks. What I'm going to see magnetically is I will see the excitations from the singlet state to the triplet state, and I'll be able to see a sort of traveling magnon-like excitation, which is where I create a triplet, and then it travels through the lattice, either in this direction or in the perpendicular direction. So all of that I will see, but everything will be magnetically in the inelastic channel.
The triplet wave, would that show up in Bragg peaks?
No, it's going to show up in excitations. So I'm going to see basically a gap in the magnetic excitation spectrum, and then there'll be a kind of a dispersive, I'll see some sort of dispersive sinusoidal wave, and the amplitude of this dispersion will tell me something about the hopping, the ability of this triplet to hop from side to side in the lattice. I will also be able to see experimentally whether I have this kind of arrangement, or whether, for example, the singlet lies here and then the next singlet lies here, for example. If there's a phase shift there, then that's going to show up in the intensity of the inelastic scattering. So it's, you can, yeah, it's, I would say that there's no, you have to work out the details and so on, but there's no question that you'll have lots of information in the inelastic scattering about this kind of situation. Now, if you ask about if you ask about a resonating valence bond state, so you would have not